All right, this is module number 16. We're talking about data structures. Why do we need data structures? We want to organize data effectively, efficiently. The data is comprised of objects, and each object is an element of a set. And ideally, to organize the data efficiently, we want a low memory footprint. We want fast accesses to the data, searches through the data, edits to the data, updates to the data. Now, if our data is static, doesn't change, it might be simple to implement this in a very sophisticated way, but typically data is dynamic. New objects come in, old objects go out, objects might be edited, and so on. So there are changes over time, and key operations are going to be insert, delete, checking membership, whether something's there or not. And if we want more operators, we may need a more refined data structure. So as always, there's a trade-off between keeping things simple and sophistication can support more types of machinery. So what does our data structure need to support? So first of all, again, the data is organized in objects. Each object is an element of a set, and each of the object contains fields. The key is a special field. It identifies the object. For example, if you're a bank, the key could be, let's say, numbers that correspond to bank accounts. So objects are going to be customers, and the key is going to be bank account numbers. Other fields could contain attributes about objects. So again, the example of a bank where these objects are customers, the key is the bank account number, and the other fields could be first name, last name, date that you opened the account, date that you had the last transaction, amount of money in your account, and so on. What are some common operators? So we have a set, capital S, and the search operator means that we're searching for an object whose key is K. Remember that the key is the special field that identifies the object. Now, what if we want to insert an object into a list or into our data structure more generally? A list is a type of data structure. So X is going to be a pointer to our object, and we're going to be given this pointer, or possibly the object itself, and we'll be inserting it in the set S. Deletion. The delete command means that we're given X, a pointer to that object. It's not necessarily the key. If all you have is the key, then first you're going to need to search, and after that, using the pointer that was returned by the search, you'll delete that object. Then we also have minimum and maximum commands. They return the smallest and largest keys in our data structure, respectively. Now, not every data structure is ordered. The ones that are ordered, minimum and maximum, make sense. The ones that are not ordered, they don't make sense. If it is an ordered set, meaning that there's an order between 1 is less than 2, which is less than 4, which is less than 4.2, and so on, we may have successor and predecessor commands that give us the next object in the structure or the previous object in the structure, respectively. But note that if you're already the last object in the structure, there's no successor, so you'll return a nil, an empty type of pointer. And if you're the first object, that's what you're pointing to in the pointer X, there's no predecessor. And again, you'll need a nil. So let's look at two different types of data structures. One is stacks and queues. We'll begin with that, and then we'll talk about linked lists. A stack is, you can imagine to yourself a stack of dishes. You're a restaurant, and hypothetically, because we're talking about data structures, when data comes in, could be a customer or whatever it is, on the dish, you jot down the data, and then you put this new dish on top of the stack. That's pushing. Popping means that you have your stack of dishes, and you pop the top dish on top of the stack. You take it off the stack. That's called popping. Okay, and then it's no longer in your data structure. So now that we understand the analogy, we always remove the last element that was inserted onto the list. The dish that's on top of the stack is the dish that was the last one that was pushed onto the stack. And this is a last in, first out order, LIFO. In a moment, we'll talk about FIFO, first in, first out. So for stacks, they're LIFO. We push or insert a new object onto the stack, in our analogy, on top. And when we delete, we pop a dish off of the stack. And a possible application would be that we have an operating system and we have a list of routines that we called. And when we go into a new routine, we we push the information that corresponds to the new routine onto the stack. So there could be variables in the new routine, local variables, and they're all pushed onto the stack. And when we exit the routine, let's say we're in routine number 3, we finish routine number 3, we remove those variables from the stack, we pop them, and then we're back to the memory in routine number 2. That's now on top of the stack. So those are stacks, LIFO, and what about queues? So for a queue, you can think of a line of customers. Again, you're a bank, and people are coming to the bank, and the last person that came in, we put them at the back of the line, the back of the queue, and when one of our cashiers or investment consultants or whatever you're processing at the bank, when one of our processing individuals becomes available, you perform a dequeuing operation. You take the person off the front of the queue, and you process them. Now, of course, our analogy to a bank can be considered as an analogy to a data structure. You have an online bank. The customers are giving you transactions, and the transactions are enqueued at the back of the queue. And when you have time, resources to process another transaction because you've finished processing one of them, you take out or dequeue the object at the front of the queue. So what we're doing in a queue, we're always removing the first element that was inserted, meaning long ago, it was inserted long ago. That ensures a style of fairness, and this is a first in, first out, or FIFO order. Again, the application could be customers that are waiting for their request to be processed. Enqueuing and dequeuing corresponds to insertion and deleting. So how do we implement these for stacks? We have an array of S with n items, 1 through n. We also need to store the top location. So if, for example, n is 7, and there are currently 3 objects in the stack in locations 1, 2, 3, then we can store the number 3. And if we're requested to add something to the stack to push, we insert it at location 4 and we increment the top. And if we, in contrast, are requested to pop, then we return the object that's currently in location 3 and we decrement top of S from 3 to 2. So operators here could be whether the stack is empty, in other words, whether the top is 0. If the stack is full, that corresponds to the top being n. Pushing and popping, as I described earlier, they include either incrementing or decrementing the top. What about implementing a queue? So again, we're storing things in n elements, and you'll note that if we store things in elements, we may have overflow. This is a finite queue, just like on the previous slide, it was a finite stack. So occasionally, if our design is poor and we get a lot more data than we anticipated, we may have a problem. This, in a simple system, this could be implemented with just like, you have an overflow, deal with it, sorry. And this in many systems, this is very real. For example, if you have hardware that's managing packets in the network, the amount of memory that you'll typically have is rather finite on such a chip. And if you've exhausted your memory, tough luck. On the other hand, there are other software systems, let's say on a computer, where it could be that originally you're allocated 10 locations in memory. And then if you hit 10, you go to 20. And if you hit 20, you go to some larger number, and so on. So occasionally you increase the number of elements, but as I said earlier, that's a more sophisticated operation. And to get more powerful data structures, we need more sophistication. So getting back to the issue of our queue, we have n elements. We're storing the head and the tail, the back and the front of the queue. Our elements begin at the head, then head of q plus 1, head of q plus 2, and so on up to tail of q minus 1. I'd like to note that the index is modulo n. So if n is, let's say, 7, and we start at 5, then we have 5, 6, 7 wrapping back to 1. If the head is equal to the q, it means that the q is empty. If the head is equal to the tail plus 1, it means that the q is full. So with these comments in mind, you can go read various textbooks, or you can think about how to implement, how to work through the details, but you can see that in queuing means that we're storing new data and we need to increment the tail. And increment doesn't necessarily mean plus 1, it means a modulo increment. And dequeuing means we're returning the data and we're incrementing the head. And once again, that increment could wrap us back from n to 1. So those are stacks and lists, or rather stacks and queues. And now we're going to talk about linked lists, which are a different type of data structure. With linked lists, we have objects that are arranged in some linear order, and they don't necessarily need to be LIFO or FIFO. If we remove something from the list, it's not necessarily the last one that was inserted or the first one that was inserted. It could be some different order. So lists are more flexible. And in an array, we're ordering objects using an index, which is an integer. And if we have an array and we want to put something in the middle, it's difficult to add an object in the middle because what does, let's say you have two indices, 3 and 4, what does it mean to put an object into index 3.6? It's in an array, we don't have a non-integer index. A list, on the other hand, we can arrange objects with pointers. The pointers can be just one direction of pointers moving forward, or they could be bidirectional or even more complicated. And it's easy to insert or delete objects by updating the pointers. So let's talk about different types of lists. A doubly linked list, each object contains a key and pointers both to the next object on the list and the previous object in the list. And you can see that the last object in the list, the 4, its next location is a nil, and the 5, the first location in the list, that object, its previous pointer, again, points to a nil. In contrast, a single linked list, we only have next types of pointers, not previous types of pointers. The last one, as before, points to a nil, but the previous one, or rather the first one, there's no previous, it doesn't have a previous pointer, and therefore the single directional list is simpler to maintain in some ways than the doubly linked list. So the single linked list, there's only a next pointer, and in a doubly linked list, they're both. And one interesting feature of lists is that if they're sorted, for either a single or a doubly linked list, you can search for the correct location where you want to insert a new object, and then you can modify the pointers of the object that should be right before it and right after it. And by some local operations, let me annotate this. Suppose that you want to add an object between the 7 and the 3. So now you're going to point to this, let's call it 12. And 12, its next pointer will point to the 3. 3's previous pointer will now point to 12. And 12's previous pointer will point to 7. So if you think about it, and I'm changing my color, of course, the two pointers that leave this new object 12 need to be updated. And we also need to update the next pointer that leaves the 7, the 12's previous. And if we look at 12's successor, the 3, or successor or next, its previous pointer also needs to be updated. So for updating operations in a doubly linked list, less than 4 in a singly linked list, as you can imagine. And in the sorted case, it'll be somewhat easier to search through that type of list. An unsorted type of data structure might be more complicated. Some operators on linked lists. So one operator is that you're searching inside a list L for the object with a key K. And of course, if that object doesn't exist, you return a nil. Now, what's the complexity of this operation? So you go to the first location of the list, and if that's the correct object with key K, you're done and you return the pointer. And if not, then you move on to the next one. And if that's the correct one, you're done, and so on. And what if you hit, let me again annotate. So this is the beginning of the list. Object number 1, object number 2, object number 3, and the question mark will be for the nil, okay? If we reach the last location and the pointer is the nil, so we search and search and search for the key K. We didn't find it, we return a nil. Now what about the complexity? So the complexity is, if we were lucky and it's toward the beginning of the list and we find it in 2, 3, 4 operations, theta of 1. But that's optimistic. In the worst case, we need to scan the entirety of the list, and that's O of n. So let's think about it. We are at least theta of 1, and at least theta of 1 means that we're omega of 1, and we're also O of n. We're definitely not omega of n, because occasionally we don't do things with order of n operations, but a few number of operations, a constant number of operations. On the other hand, we're definitely not larger than n. So we're somewhere between constant and n. And the average case, depending on specific assumptions, the average case might be proportional to n. But what we do know is that we have a worst case O of n. It's not theta of n because this could be constant time. So that's one operator. What about inserting things to the list? So we have a new object, and if we just want to put it in a location that we're already aware of, that takes theta of 1 time, because as I said, we just need to modify 4 pointers for the doubly linked list, less than 4, I believe 2 for the singly linked list. Now this assumes that we have a pointer. If we don't know where it is already in the list, then we need to search, and again, that could take O of n time. Deletion, again, we have a pointer, and let's annotate this for the example of a doubly linked list. So let's say that we have forward pointers, and we have previous backward pointers. And one of the locations here in blue is about to be deleted. That's X, the pointer to this guy. So by deleting it, of course, that object can be removed from memory, but what about the pointers? So we need to traverse the pointer to the next, and now its next needs to actually point to this guy. So that's one pointer that needs to be modified. This pointer, of course, goes away when we delete the object. And then what about the next pointer? So of course it'll be deleted, but when we get to this guy, we need to point back. So we have 2 pointers that need to be edited, modified, 2 pointers that will be deleted as part of the object. So overall, theta of 1 and some splicing off of the data structure is necessary here. So that'll be it for module number 16. We'll continue next time.